the figure. It's standard procedure solving this type of problem. We will first compute the variables of the leading motion, acceleration and velocity. Okay, so leading motion of the workpiece, of course. And I will just underline it again in purple. Okay, to do that, we are assuming, yes?
I just have one quick question. Where's the angular velocity in this diagram?
Omega, I didn't draw it because here in the, because we don't have to compute it, but we can include it. So if we have the acceleration, angular acceleration given with direction, then our angular velocity would point this way.
And a follow-up. So the VR in the second diagram is what we studied in the circular motion, right? The last week.
Yes.
Understood. Okay. Thank you.
Okay. Yep. Okay. Our leading motion, to compute the values of the leading motion, we are freezing the relative motion, meaning that we assume that there is only the leading motion. Okay. So our block moves, including the arm, move rectilinearly, and we reach this dotted position. Yeah. So freezing relative motion refers to we are only considering the leading motion, so no rotation in our system. Our leading motion is rectilinear. The leading acceleration is given with 2 meters per square second. If we know the acceleration, we can compute the velocity. First page in our formulary, we have the initial velocity plus AL times T. And in the problem description, it's stated that our system starts moving from rest position, meaning that the initial velocity is 0. So this cancels. So we have 2 meters per square second multiplied by 0.8 seconds. So 2 by 0.8 is 1.6 meter per second. Okay, and then we could compute the distance traveled. It's not asked for, and that's why I will write it in parentheses. But just to have the complete information, we could compute the distance, which is 1/2 AL T square, so 1/2 times 2 times 0.8 square, which is 0.64 meter. Okay, that's all we have to do for the leading motion. Then let's discuss the relative motion. So same procedure. In case of relative motion, we are freezing the leading motion, meaning we are assuming that there's only a rotation of the workpiece about the sliding block. Okay, so this is a circular motion. Alpha is given with 3 per square second. We can compute omega, the angular velocity from there. Again, there's no initial velocity, so the first term cancels. And then we have 3 times 0.8, which is 2.4 per second. And for the angle, we have to integrate once more, 1/2 alpha r t squared, and this results into 0.96 radians, which is equal to 55 degrees. Okay, now we cannot do the vector addition of our acceleration with angular acceleration. That doesn't work. The dimensions don't match. So we have to transfer these circular variables from the circular motion into our standard variables, acceleration, velocity, position. And for this, we need this last few formulas on the first page of the formulary, and we can compute tangential and normal component of the acceleration. I will state it here, because otherwise you will not see the, well, it moves out of your screen, all my writing. So A R tangential component of the relative acceleration is computed by alpha r times radius, which is r in our case, these 0.5 meters, as given in the problem description. So this is 1.5 meter per square second. AR normal, omega r square times radius, which is 2.88 meter per square second. Then the velocity, omega r times r, is 0.2 meter per second. Angular velocity times radius. And now we could compute the arc length. It's not asked for, but to state all variables, that's angle times radius, and this is 0.48 meter. And here it's important to use the angle in radians and not in degree. Yeah. Radians times meter gives meter. Okay, now we have the variables of leading and relative motion. We might have to think about Coriolis acceleration. I will include it here below. So this could be the third part
Excuse me, Professor.
Yes.
I just have one question. So I'm a bit confused in between this VR, which to me is the normal, let's say, velocity along the circular path, and then there's a relative velocity. Are they the same, or?
The VR is the VR drawn in the figure here, the relative velocity. Since our circular motion is our relative motion is a circular motion. So the R stands for relative motion. And in our case, our relative motion is a circular motion.
Okay, understood. Thank you.
Okay. Okay, Coriolis acceleration. Well, in general, the Coriolis acceleration is 2 omega L VR, but in our case, it's 0. Since our leading motion is a rectilinear motion, so there is no leading angular velocity. Okay, now we do have our components, our vector components, and the last step we have to do is compute the absolute velocity and absolute acceleration. Now, we can actually use red. And so to make it easier to understand, to see, I will just copy the two figures above, because otherwise I will have to move up and down all the time. So just a second. Okay, there's a question. There is no Coriolis acceleration because this value is 0. There is no leading angular velocity. Our leading motion is a rectilinear motion, straight along a straight line, no rotation. And if there's no rotation, then there cannot be any angular accelerations or velocities. So this is 0, and that's why in the result, the Coriolis acceleration is 0 as well. Okay, so now we have to do the vector addition, and we will start with the velocity. For this, again, same as for the absolute acceleration in a circular case, or same as statics, engineering mechanics 1, we have to decompose our vectors into, for example, all horizontal and vertical components, sum these components, put the square, add them, and put the square root. Just to remember, forces, the resultant force is sum of all forces in x direction plus sum of all forces in y direction, building the squares, adding them, building the square root. We will do the same for velocities and acceleration. But of course, the math behind is the same, as you already know. Okay, for the velocities, we only have 2 components. And I will just write here to just that I don't have such a big gap. So our velocity in the square root, and then I will start with horizontal components, and then with the vertical components. Okay, for the horizontal components, we do have the full leading velocity vector. And we do have the component of the relative velocity, the horizontal component of the relative velocity vector, pointing to the right as well. So it's v plus VR cosine phi r, and then building the square. And then there's only one vertical component of the relative vector, a relative velocity vector, pointing downward. So it's VR sine phi r squared. Okay. We do know all these components. We know the velocities, we know the angle, and then we can just apply the variables to our calculator, and we obtain 2.49 meter per second. Coriolis acceleration is a pseudo acceleration that keeps our point on track in case of a leading circular motion. Because we have to consider the circular motion when describing leading and relative on its own. Our observer, our moving observer, moves along a circular path. We have to consider that, take that into consideration. Okay, same for the accelerations, only that there we have 3 vectors instead of 2. So again, I will start with the horizontal components. We have the leading acceleration. We have the tangential component of the relative acceleration pointing to the right as well. So it's positive plus AR tangential cosine phi r. Maybe for the ones who still have trouble finding the angles, I will include them, but you probably should be used to that from statics as well. But here they are. Okay. AR cosine, and then the horizontal component of the normal relative acceleration points to the left. So it's negative minus ARN sine phi r, and we build the square root. Okay, and then the vertical component, I assume pointing downwards as positive direction. Both our components point downwards, so they are both positive in our equation ART sine phi r plus ARN cosine phi r. Okay, and then again, we have all the individual variables. We apply them to the calculator and obtain 2.92 meters per square second. If we would have a Coriolis acceleration, we would have computed the Coriolis acceleration and included it in our absolute acceleration. It would have been another vector. Remember, statics, the procedure is the same, no matter if you have 3, 4, or 5 forces. The procedure doesn't change. It would just be an additional vector. And that's the same here with the Coriolis acceleration. Okay, any questions?
Professor, the phi in this case, was it found using the equation of phi is equal to half alpha times t square?
Yes, this one.
Okay, yeah, perfect.
Yeah.
Got it, thank you.
Okay, you're welcome. Are there other questions? Okay, so I will just repeat our standard procedure. We have a point mass. We have to see that, we have to understand that. Okay, we have a point mass. And in case of a point mass, these formulas are not available. Which ones? These? Well, no, they can't be because they are different for every problem. But everything else is. But how you, well, it depends on the precision of your vectors, direction, angles, etc. Everything else is here. Circular motion, then the above the rectilinear motion, then the important parameters to compute from circular to rectilinear values. And if we move one page further, we have the general motion here, absolute velocity, absolute acceleration, Coriolis acceleration. So this is all here, but how to obtain, how to derive the vector itself, depending on the direction, this depends on every problem. It's different for every problem. Okay, so you have a problem given. You have to decide which one is your leading motion. Once you found your leading motion, you have to decide, is it a rectilinear or a circular motion? Then you compute the values for your leading motion, either rectilinear or circular, can be both. Then you step onto your moving object, your leading motion. You are a moving observer performing the leading motion, and you have to decide which one is your relative motion. Is it a circular or a rectilinear motion? It can be both too. Okay, so then you compute the values for the relative motion. Then you have to decide, is your leading motion a circular motion? If so, you have to compute the Coriolis acceleration. If you have a figure including all your vectors for velocities and acceleration, you need this figure to solve the problem. Otherwise, it will not be possible to obtain the correct solution. If you have this figure with all your vectors, then you have to build the absolute vector for velocity and acceleration, choosing two directions that are perpendicular to each other. Most often it will be horizontal and vertical direction. And then you do the vector addition, just like that. Okay.
I have a question.
Yes.
For this example, understand everything. I understand the F calculation, but I just want to know, how do we know for this question, the leading motion is rectilinear and the relative motion is circular?
In this specific question, yes.
Yeah. How do we know that?
Yeah, okay. Okay, let's do another example. Exercise 1.9. So there it is. We have a platform that rotates with a, here again, it's described in the text and it's drawn in the figure as well. And you always, that's also an important part. You have to read the problem description carefully because there's a lot of information that helps you solving the problems. So if you only have a look at the figure and start computing, you might miss information you need to obtain the solution. So, okay, here, the platform is rotating with constant angular velocity, omega L. And then there's a person walking on this platform with constant angular velocity, omega R. In a circle relative to the platform, radius is given in constant. And we have to find the velocity, absolute velocity, and acceleration of this person. Okay, what do we have to do? We have to draw two figures, one for the velocities and one for the accelerations. Now, you do not have to draw the entire platform with the person, etc. You can, of course, it's not wrong, but we can make it a little bit easier. We draw this hinge support, and then our person, and this is R. So, and then we draw one figure for the velocities and one for the accelerations. Okay, like this. Okay, now we have to decide which is our leading motion So we are the outside observer, and what we see is the rotation of the platform, the circular motion of the platform. So this is our leading motion. Then we step on the platform, and what we see is this person. We are rotating with the platform, and we see this person walking along a circular path. So our relative motion is also a circular motion. And also, of course, it's given in our figure because there's an omega given. And if there's an omega given, it has to be a circular motion. Okay, then we have to draw the velocities and the accelerations of both motions into this figure in our point P, the current position of our person. I will give you 5 minutes time to do this on your own. Okay, try to draw the vectors in the correct direction, and then you can see the solution. Okay, but just try it on your own first. Okay, let's have a look at the figure. So I will first draw the leading motion. This is our direction of angular velocity in both cases, of course. And then we have a velocity vector pointing tangential on the path in direction of travel. So this would be the direction of the leading velocity, perpendicular to the radius. And exactly, you are already discussing this in the chat. Omega is constant, so the angular acceleration is 0. We can neglect the vector right away, or we can just draw it in the figure and then state later on that they are 0. So both ways are correct. And I will draw them all in the figure, and then we will talk about this in the solution. So we have a tangential and a normal component of leading acceleration. Then for our relative motion, so we have omega r pointing in same direction, meaning that the relative velocity vector points in same direction as well. Tangential on the path in direction of the leading velocity. And for the acceleration, it's the same. We have a relative tangential and a relative normal in general. Now, our leading motion is a circular motion. So we do have to think about the Coriolis acceleration. We have to include the Coriolis acceleration in our figure. So how do we find the direction of the Coriolis acceleration? We use the right-hand rule. Again, similar to statics, to engineering mechanics 1. So use your right hand. Your thumb corresponds to the axis of rotation of the leading velocity. Just a second. Right-hand rule. Thumb corresponds to omega L, axis of rotation. Then your forefinger corresponds to the direction of the relative velocity. That's an O. Forefinger corresponds to the direction of the relative velocity. And then the middle finger corresponds to perhaps the Coriolis acceleration. So the middle finger gives you the Coriolis acceleration. So now your thumb points upwards. Your banded fingers point in direction of omega L. Same as in statics when you computed the moment. Okay, so thumb points upwards. Your index finger in direction of the relative velocity, and your middle finger shows the direction of the Coriolis acceleration. Just need another color. So this way. Okay. Axis of rotation. Hot rotation. Okay, now as some of you have already noticed, omega, leading and relative omegas are constant, which means that the angular velocities are 0. Since our tangential components of the accelerations are computed by alpha times radius, they are 0 as well. A leading tangential and a relative tangential R0. Okay, and then we will follow our standard procedure, deriving the individual variables for leading motion, relative motion, and absolute motion. Here are no numbers given, so our result have to depend on the variables given, which are omega L, omega R, and the radius. So our results have to depend on these three variables. Okay, I will give you 15 minutes time to solve this problem on your own. I will open the breakout sessions if you like. You can just pick one with your friends maybe and go there to solve the problem. You can also solve the problem on your own. If you have any questions, call me into your breakout session or just or ask me if you're in the main session, whatever, or write in the chat. But remember, I cannot read what you write in your breakout session chats. Okay. I'm holding a gun. Oh, yeah. Okay. I don't know, like this. You have your fingers like the coordinate system, X, Y, and Z axis. Okay, so they have to be perpendicular to each other. Just a second, I will show it in the video. So like this, okay? And your thumb is your axis of rotation. So in our case, our leading angular velocity goes counterclockwise. Our thumb points upwards. Okay, so you did this in statics to decide whether your force acts positive or negative for the moment that you computed. Okay, so in our case, points upwards. Then your index finger corresponds to the direction of the relative velocity, so perpendicular to the radius in our figure. And then the middle finger gives the direction of the Coriolis acceleration, like this. All three fingers have to be perpendicular to each other, like the coordinate system X, Y, and Z axis. Okay? Okay. Good. I will open the sessions 15 minutes so that we have a little bit of time to discuss the solution. And in case of problems, ask me right away. Don't wait until the end. I will reply to the question in the chat a few seconds when everybody has returned. Okay, there's a question in the chat asking what happens if the calculations are wrong, but the equations are correct. So the most important part when solving a problem is deriving the correct figure, including all variables of interest. And then when you start doing the computations, I recommend to stick to variables as long as possible. So write omega, r, alpha, etc., whatever you need, okay? And then insert your numbers at the very end, like in the last line of your equations. As long as you do your calculations with variables, I'm able to follow your calculations. I'm able to see mistakes you make, and then you might miss a point for a mistake on your way through the problem. But if you continue on the correct track with your wrong value, for example, your wrong equation, you will get points for that as well. But once you insert numbers, I'm not able to follow your equations anymore because I do not know if you use the wrong equation or if you just made a mistake in your calculator, typed in a wrong number or whatever, then I'm not able to give you points after that. So it's always better to use variables as long as possible, okay? And then you will get points for that. If your value at the end is wrong, of course, you will not get a point then, but you can still get most of the points. Okay, so I hope that answers the question. Okay. So let's have a look at this problem. So it was, here there are no numbers given, so it should have been quite easy. We had to look up the equations from the formulary for the normal component of the acceleration and the velocity and the Coriolis acceleration, since our tangential accelerations were 0. So we have these 5 results for the components, and then we have to do the vector addition. And in general, this is our equation. And if you have to solve such a problem, it is important that you state this equation here, the vector equation. And it's important that you have vectors above the variables, because otherwise it would be a simple addition, which is wrong. So for simply typing an equation that is stated in the formulary, you will get points for, okay? And also it helps you solving the problem correctly. In our case, it's quite simple. For the velocities, both vectors point in the same direction. So our vector addition results into a simple addition, leading plus relative velocity, which is at same radius, omega L plus omega R. And for the acceleration, again, our tangential components are 0. And the other 3 components also point in the same direction. So again, it's quite a simple addition, leading normal acceleration plus relative normal acceleration plus Coriolis acceleration. And then, well, we can just, again, write like this. We have omega L square plus omega R square plus 2 omega L omega R, like this, which is good enough. For an example, you do not have to simplify any further, but of course you can if you like, and then you might see that this is a quadratic equation which you can also write like this. But again, it's not necessary. The previous equation also only contains the variables given. Okay. Any questions?
Excuse me, Professor.
Yes.
Do you have to resolve it in terms of horizontal and vertical?
In terms of what?
Horizontal and vertical, like we did in the previous question.
Oh, no, I don't, because I do not have any information. We could have derived the vectors, but I don't have an angle given and I have no radius. But so you probably did that. That's the radius. Then you had an angle here. And our resultant acceleration points that way, then you can derive this in terms of the angle phi as well for horizontal and vertical component.
So if in the question we are given the angle and the radius, then we have to resolve it.
No, not necessarily. Because we have to find the absolute acceleration. That's what we did. We do have the absolute acceleration. If you derived it, decomposed it into horizontal and vertical components, then you probably had something like this at the end: a horizontal square plus a vertical square. And then you should have ended up with this equation as well. Of course, the vector itself is of this size. Only the orientation in our plane is not known. But usually we are not asked to compute that. So the angle over the, with respect to the horizontal, for example. So you still, even if you decomposed your vectors in x and y, for horizontal and vertical, your final result should be this.
Okay.
Okay. Okay. There are problems. We will see that later on in our classes. There it's asked for finding horizontal and vertical component of the acceleration. Then we have to decompose the absolute acceleration. But as long as it's not asked for, we do not have to. Okay, other questions? Good, okay, if not, we will have a few more exercises regarding chapter 1 that we will do in class. And then on Friday, since our Friday class is our theory class, I will solve another problem for you. And then we will continue with chapter 2, rigid bodies. And we will discuss our standard approach there and then apply all these problems and practice these problems in our Monday class again. Okay, then have a great week. No, it's Monday today. Have a great week, and then see you on Friday.
Yeah, I have a question.
Thank you, Professor. Oh,
Yep.
Can you talk about exercise classes? Like, if there will be a section where we solve only exercises.
Well, what I will do, or what we are doing, is on Friday, all the students are in one class, in one online class. So I will focus on theory there. We will do some problems, solve some problems as well, of course, since we do not have that much of theory. But in our Monday classes, I will give you time to solve problems. Of course, I will tell you, please solve problem number whatever. And then I will give you time to solve it, or I will tell you, like, here, just draw the figure, and then we will discuss the figure and solve the next part, etc. And then this will be time for you to solve problems on your own on Mondays. Ask questions if you have any, of course. And is that what you mean?
Yeah, it's okay.
Okay, perfect. Yes.
Can you please show the today's relative motion slides? Missed something. The first 10 minutes.
The first problem we did.
No, I missed first 10 minutes of the lecture. What did we need?
Oh, sorry, I already erased this because I have to redo it right now. It's not there anymore.
Okay, Amit, thank
Yeah, maybe ask a classmate.
you. Okay.
Okay.
Excuse me, Professor.
Yes.
Are we having tutorial at 2:50?
It's not a tutorial. It's the same class as this.
Okay.
Okay, I will just.
So we are not having external tutorial.
No, there's no external tutorial this semester.
Okay, thank you.
Okay. Okay. Then again, have a good week and see you on Friday. Bye.
Thank you.
Thank you, Professor. Bye.
Bye.